So hello everyone, my name is Antonin Berthelot and I work here in Brussels at the Belgian Institute for Space Aeronomy. Today I'm going to talk to you about stellar occultation, scintillation, and also the sort of validation that we did using GOMOS data of stellar occultation. Right, so for those of you who played the game and want to improve their scores, you should pay attention to the first slides because I'm going to give you some tips. This is the basic principle of a stellar occultation. Basically, you're looking at a star through the atmosphere, and as the satellite is moving, you see different layers of the atmosphere, and from this you can get profiles of different species. On the right side, you see what ALTIUS will actually give you at L1 level. This is a snapshot of a star, so I hope you can see it from where you are, but there's just one tiny dot here at the middle because a star usually is 1 pixel and maybe the one surrounding it. Also, this is at 310 nanometers, so it gets absorbed quite fast, and below, say, 40 kilometers, it starts to become indistinguishable from noise. It's actually easier to work in transmission. So here you have an animation with 5 different wavelengths. So this is typically what we would get with ALTIUS. And you can see that in the UV, the light gets absorbed at higher altitude, so you have better sensitivity using these wavelengths. And if you want to see something around 20, 30 kilometers, then you need to go to visible measurements. And what is scintillation now? So it's a random perturbation of the air density, mainly because of gravity wave and turbulences, that causes fluctuation in the atmospheric refractivity. You can actually see it from the ground. So here's a GIF I took from Wikipedia on the right of Sirius. And you can see that the light fluctuates. You can't see very well, okay. And when you want to know your transmittance, it basically comes as an additional term here. So your star signal is basically a combination of the out-of-atmosphere spectrum, the transmittance due to ozone, for instance, refractive dilution, and then scintillation, which comes as an additional modulation. GOMOS had a fast photometer, so working at 1 kilohertz to measure scintillation and actually help them mitigating its effects. And you can see here how fast it oscillates and how strong this can be. So the good thing is it's a random perturbation, so if you integrate over a slightly longer time, then of course the effect gets smaller. This is our end-to-end simulator. So basically we just start with the atmosphere and species density. We use our radiative transfer model to generate scenes, and then we have a synthetic L1 generator to have L1 observations such as we would have them once ALTIUS is flying. This is the L2P, so this is a bit complex, but basically you just generate transmittance from the L1, and then you choose measurement vector, how you combine these transmittances, and you try to retrieve ozone, so you adapt your synthetic measurement vector until you reach a good agreement. And what comes out of this is our L2 product. So the story is the same for all species in stellar occultation with scintillation, but I'm going to only talk about ozone today. Right, so there are a couple of differences between ALTIUS and GOMOS. The main, primarily, so ALTIUS is intended to be quite flexible, as you've heard already, and to work mainly in brightline, but also in occultation, while GOMOS was intended primarily to work in stellar occultation. And this is the reason why they put the high-frequency photometers to help them with scintillation. Our L1 product will be 2-dimensional snapshots at given wavelengths, while GOMOS had a full spectrum, but only over tangent altitude. And the spectral range is quite similar, but ALTIUS will have 3 channels measuring simultaneously. Right, so if we go back to this scintillation, this is now plotted over time, and what we want is to be able to distinguish what is due to simply transmittance, etc., from scintillation. So we use this technique, singular spectrum analysis, to generate this black curve of low frequency variations. And then we get the high frequency variations from scintillation. This is done to simulate the effect of scintillation on our measurements. Then we integrate it, so typically we have 0.5 second measurements with ALTIUS, and we get this scintillation factor out of it. So you can see that above 30 kilometers the variation is quite small, but as you go lower into the atmosphere, then it gets worse and worse. As I said, because it's a random perturbation, if you integrate longer, then the scintillation factor becomes smaller and smaller, but there's of course a trade-off because you have then less measurements since stellar occultation are quite fast. Right, now if we go back to our end-to-end simulator, we can simply add scintillation to our scenes using this simulator. And we now have to pick a measurement vector, so a kind of naive approach is to use these 5 wavelengths and simply use the transmittance. You can also use doublets, so we tried this one, so it's with the same wavelength. And then you also have this second doublet configuration, which I'm going to explain now. So as I was saying, ALTIUS has these 3 channels. So you're able to measure simultaneously at different wavelengths, but only if they're measured by the different channels. So with this configuration, we're actually able to always divide by 1 wavelength that is measured simultaneously. So 310 and 442, for instance, and then 320, etc. And the reason why we do this is because, so this is taken from a paper of Victoria Sofieva, but you see that there's quite a strong correlation between the scintillation factor at different wavelength. And this is more true for vertical occultations because all the wavelengths kind of see the same perturbation. And as the occultation gets more and more oblique, it's less true. So now, basic retrieval. So this one is without radiometric noise because I simply wanted to see the effect of scintillation on our retrievals. You have a true ozone here, it's the black curve, and then what we would get without scintillation and a basic transmittance measurement vector. So it's an almost perfect match because there is no other source of noise. And then I tried the 3 measurements vectors that I mentioned before. So you have transmittance and the first doublet, and you can see they don't perform very well, so they have quite strong oscillations around the true ozone value. And if you use this second doublet configuration, you're actually able to reduce the amplitude of these oscillations. Of course, the correlation between the scintillation factors at different wavelengths is not perfect, so you still have some remaining scintillation left. And now what we want to do is to actually use the data from GOMOS, so the full transmittance, not just the high-frequency photometer. So we don't need our RTM anymore to generate the scenes. We just take transmittance and star spectrum from GOMOS L1 product. We also use their pressure and temperature profiles from the L2 to insert it into our L2 processor. You have here transmittances from GOMOS, so at 4 different wavelengths, and you can see a bit of this scintillation effect, I believe, here at 442 nanometer. Then I picked about 7,000 observations from the 2006 observations. I chose the 22 brightest stars with a temperature above 5000 Kelvin just to have some measurements in the UV. And this is the coverage that you get over the year 2006. You can see here the South Atlantic anomaly, where you have no measurements. And now, if I use this basic transmittance vector, I can compare it also to this synchronized doublet. So you see that the error overall gets a lot lower, especially here, around minus 70 degree latitude. So we are quite happy with these results, even though we still see here and there a couple of points where the agreement with GOMOS is not great. But typically we are around 10% error. And if I go to the different altitude bands, because these are profile retrievals, so same with the transmittance and the synchronized doublet, I see that it gets better with the doublet, but we still have here some strong deviations around, so between 20 and 25 kilometers. But we are quite happy with the results here because we see that for most stars below 10 kilometers, the agreement is quite good with GOMOS. So this is quite good news for us because we don't have a high frequency photometer on ALTIUS, which means that we have less information than GOMOS had to perform the retrieval, and we still manage to kind of be there. There are other reasons why we could have these strong errors here, mainly that we have not included yet the aerosol extinction in our retrieval, so we expect this to get better once we actually take care of the aerosols. Also, we have quite a strict rejection criteria on the measured transmittances, so below 1%, for instance, of transmittance, we just discard the values, meaning that here at low altitude we have less data points. Right. So in conclusion, if we carefully choose our doublet, we are able to mitigate scintillations, and we're quite happy with those results. There are still some things to improve. For instance, this doublet uses data at 442 nanometer. So there's an interference with NO2, and we want to improve a bit on this. Okay, and against GOMOS data, we actually perform quite good, I think. It's very important for this to work to be able to synchronize the snapshots to make sure they're taken exactly at the same time and integrated over the same time. We also did some tests on this to estimate what the maximum deviation from perfect synchronization could be. And in the future, we want to couple this ozone retrieval with an aerosol retrieval in order to get better accuracy, especially in the lower part of the profile. And we could also think of adjusting the regularization based on how strong scintillation is, because it's basically just added noise on your measurement. So we could think of having stronger regularization for more oblique occultations. And with this, I'd like to thank you for your attention and show you again ALTIUS.